Hi, I'm Dr. Jason Brinkley, and this is Oxidation Reduction Processes. By the end of this video, we will be able to write oxidation and reduction half reactions and identify oxidizing agents and reducing agents, compare and contrast voltaic and electrolytic cells, and describe examples of redox processes. Redox is the term used for oxidation reduction processes. Oxidation is the loss of electrons or increase in oxygen content. Reduction is the gain of electrons or increase in hydrogen content. Recall from previous videos, oil rig or Leo goes grr. Oxidation is loss, reduction is gain, oil rig, or lose electrons oxidation, gain electrons reduction, Leo goes grr. And you can't have one without the other. You can't have oxidation with no reduction. You can't have reduction with no oxidation. And since they go together, we can split these couples into half reactions to describe the process. So for example, we've got magnesium chloride being made from magnesium and chlorine. The magnesium goes to magnesium 2 plus 2 electrons. This is losing electrons, so this is oxidation. Chlorine gains 2 electrons from the magnesium to form 2 chloride ions. So this is gaining electrons, this is reduction. If you add the two together, notice the electrons cancel, and we're left with magnesium plus chlorine goes to magnesium chloride. Really what we should do is we should write this as MgCl with 2 in front. MgCl2. Because magnesium is a 2 plus. MgCl2. So this is the oxidation half reaction. This is the reduction half reaction. We define the oxidizing agent as the substance that causes oxidation. If you cause oxidation, you yourself must get reduced in the process. Okay? And we define the reducing agent as a substance which causes reduction, thereby getting oxidized in the process. So the oxidizing agent is reduced, it gains electrons, and it causes oxidation. The reducing agent is oxidized, it loses electrons, that's what oxidation means, and it causes reduction. So in our previous example, boy, I'm just batting 1,000 this morning. Plus Cl2 goes to MgCl2. Magnesium got oxidized. Therefore, it is the reducing agent. Chlorine got reduced. Therefore, it is the oxidizing agent. Okay? Write the oxidation half reaction, the reduction half reaction, and the complete reaction for the formation of calcium sulfide from the elements calcium and sulfur. Remember, the electron gain must equal the electron loss. So let's write the first complete reaction. Calcium plus sulfur goes to calcium sulfide. How do I know it forms calcium sulfide as CaS? Remember that calcium forms 2 plus ions, sulfur forms 2 minus ions, therefore it is CaS. So the oxidation half reaction, who gets oxidized, who gets reduced? Well, calcium forms a plus 2, so calcium goes to the calcium ion plus 2 electrons. And then the sulfur gains 2 electrons to become the sulfide ion. So here's our oxidation half reaction. Here's our reduction half reaction. Who gets oxidized, who gets reduced? Calcium gets oxidized, sulfur gets reduced. Who are the oxidizing and reducing agents? Calcium gets oxidized, therefore it is the reducing agent. And sulfur got oxidized or reduced, so this is the oxidizing agent. They're just the opposite of each other. Okay? So, identifying the oxidizing agent, reducing agent, the substance oxidized and the substance reduced in the reaction described in question 8.21, we just did. All right, what is a cell? A voltaic cell is an electrochemical cell that converts chemical energy into electrical energy. Think like a battery. This is a spontaneous process that occurs when you form a circuit. Okay? And it consists of two half cells, the oxidation half cell and the reduction half cell. We call the oxidation half cell the anode and the reduction half cell the cathode. You can remember this as anox stares at the red cat. Anode, oxidation, reduction, cathode. So here we have the copper zinc voltaic cell. The way this is set up is we've got zinc anode inside zinc sulfate solution. We've got a copper cathode inside copper sulfate solution. We've got a salt bridge which allows for the charge to flow. And then we've got this hooked up to a voltmeter which measures the voltage of the cell. Now at the anode, the zinc gets oxidized. At the cathode, the copper gets reduced. So what happens is the zinc actually comes off of the anode and starts becoming part of the solution. The solution gets more concentrated in zinc. Okay? And the zinc anode actually becomes lighter. It loses mass to the solution. At the copper cathode, the cations are attracted to that negative charge that's coming off of here to be reduced, okay? And the solution, the copper solution, becomes less concentrated, and the copper cathode becomes heavier. It gains mass from the copper in solution, okay? And this process produces 1.1 volts of electrical energy. Okay? Now, electrolytic cells, on the other hand, use electricity to cause a non-spontaneous chemical reaction to occur. It is the opposite of a voltaic cell, and it's often used in rechargeable batteries and electroplating. Okay? So electrolytic cells is basically the reverse process of a voltaic cell. It's causing something non-spontaneous to occur. So here we have a comparison between a tin 2 copper cell, where the oxidation half reaction is tin goes to tin 2 plus 2 electrons. The reduction half reaction is copper goes to copper metal. And the overall reaction is tin plus copper goes to tin ions and copper metal. The reverse, and the electrons flow from the anode to the cathode. In this cell over here on the right, the electrons flow from the now anode to the cathode, but the anode and cathode are reversed. That is because we have an external battery producing an overpotential greater than 0.48 volts. That's what the voltage you get from that cell is, 0.48 volts. If I add something more than 0.48 volts, if I add 0.49 volts, I have the reverse reaction becoming the predominant reaction. You have an oxidation half reaction, as copper gets oxidized to copper metal to copper ions, and tin gets reduced to tin metal. Okay? And the overall reaction is the opposite. This is my electrolytic cell. This is my voltaic cell. Now, redox processes are occurring all the time. Okay? Corrosion, rusting. This is a major redox process that occurs all over the country, all over the world, and actually accounts for a large amount of the chemical industry trying to prevent corrosion from occurring in metals. It's huge. It's big business. Coatings for corrosion, anti-corrosion coatings. Combustion reactions are also redox style processes. So every time you burn a log or you burn fossil fuels, that is a redox process. Bleaching, metabolism, antiseptics, antimicrobials, all of these are redox processes. So metabolism we don't really think of as being a redox process, but here we have ethanol plus liver enzymes going to acetaldehyde and to acetic acid, and then finally to carbon dioxide and water. The carbons are being oxidized because they're gaining oxygen content. Whereas the oxygen here gets reduced as it gains hydrogen content. Okay? So, metabolism, redox process that is vitally important. I hope you've enjoyed redox processes and get out there and do some redox chemistry of your own. And I look forward to seeing you in the next video.